Alright, you guys, so I just wanted to film a really quick video after grading our CER statements. I think there's a little bit of confusion, in particular if you did water or ice melting into water, and also if you did salt dissolving ice or putting salt in water or something like that. Those ones were tricky. They were pretty nuanced, and I think they kind of seemed like they were the easiest ones, but in reality I think they were actually pretty challenging. So I just wanted to go over that to give you a little bit of feedback. In a video form I gave you some feedback on the assignment itself, but here we go. So just a reminder, endothermic and exothermic are going to be talking about input versus output of energy. We are talking specifically about the reaction itself, not you. Okay, so if you have to exert energy to put salt into water, we're not talking about that. We're only talking about the salt and the water particles themselves. So just a reminder, breaking a bond requires an input of energy. Okay, we want to think about breaking a bond like pulling apart two magnets. Pulling apart two magnets, they are attracted to each other, so you have to exert energy to break that bond, and this would be considered endothermic. Later in this week, so before, when I originally did this, you didn't know this at the time, but this is also true not only for breaking bonds, but also for breaking intermolecular forces, and that's going to be really important here in just a minute. So remember, intermolecular forces, or IMF, function like a bond in the sense that usually we are talking about charges that are attracted to each other, either full charges or partial charges, which we use that delta sign. Okay, forming a bond, we are putting two things that are attracted together. Well, that releases energy because it's energetically favorable for those two things to come together. Okay, so this is what we'd call exothermic because it's releasing energy. This is the same thing with intermolecular forces as well. If you break an intermolecular bond or force, that would be endothermic. If something's coming together, that would be exothermic. So let's go through an example with, let's do ice melting. Okay, a lot of people did this example of ice melting, and they were talking about if you put ice in water. Okay, so in this example, there's really kind of two things happening here, and I would encourage you to think about it from the perspective of the ice as well as from the water, which sounds kind of interesting. But here we go. We know that with the ice, water molecules are together, okay? They're together by their intermolecular forces. So if these are water molecules, we know that there are forces of attraction here, and actually hydrogen bonds, which are pretty strong. So there are, I'm going to put H bonds for hydrogen bonds, and this is intermolecular forces in between these water molecules in the ice. Okay, these are very strong, and there's lots of them, and that's what makes this ice. Okay, it's a solid form. But in the water, there are still intermolecular forces happening, but there's fewer, and they're a little bit more spread out here. So maybe there's one weakly there and maybe another one, I don't know, over here. Okay, so there are H bonds, hydrogen bonds, but they're less or fewer of them in water form. I should probably not say water, I should say liquid. Okay, so what happened here? As the ice melts, what's happening is these bonds, these intermolecular forces, they're not really bonds, but they're hydrogen bonds, these are being broken. Okay, so I'm going to write down hydrogen bonds break, that equals melting water. Okay, if we are breaking a bond or a force, is that exothermic or endothermic? We know that breaking a bond requires an input of energy, which is endothermic. Input energy. Okay, so ice melting is endothermic because you have to input energy to break the bonds of the water molecules so that they're more in this form, which is the liquid water. So that would make ice melting endothermic. Now, a lot of people said, well, the water surrounding, like if you put an ice cube in water, the water was warm and then it got colder. And because of that, you pictured, which is true, like you had the right thinking, you pictured this graph where we had energy and time. You had a starting temperature and it ended up being lower at the end. So you said, hey, isn't this exothermic? And you're right, this is exothermic. The problem is, this is talking about the water and not the ice. So for the water itself looks like this, but as it gets colder, it actually starts to form more hydrogen bonds because those molecules can get a little bit closer to each other. Oops, my diagram's getting a little crazy here. So because of that, the water getting colder is exothermic, but the ice melting is endothermic, which is really confusing. Most people were talking only about the ice, and that's really all I was looking for here. You don't have to talk about both situations. But the ice itself, when you are breaking intermolecular forces with those water molecules, that is an input of energy, making it endothermic. So that's really what I was looking for here. I want to do one more example. If you did this, you can keep watching. And that is salt and water. Okay, this one also is pretty much the same idea. It's a little bit more challenging. So we know that salt is an ionic compound, and we still have water here. Water also here is in this kind of dipole-dipole hydrogen bonding interaction. Intermolecular forces are going on. Okay, this isn't a really great diagram. But we know that there are intermolecular forces going on. When you put the salt in water, the solution actually got colder, which is pretty interesting. You already know, because it got colder, that this is going to be endothermic, that there's an absorption of energy here. So because of that, what's actually going on is that the salt is disrupting the bonds here. These bonds are being disrupted by the ions. And so because we're breaking those bonds, I should have drawn them the opposite direction. That's okay. You get the idea. Because we're breaking those bonds, there's an input of energy. Now, you could also say, in the same sense, that there is an output of energy when you form new attraction here between the water molecules and the ions themselves. So again, this one is kind of challenging because there's really both going on in this scenario, okay, with salt and water and with ice melting. So here you can talk about how the salt disrupts the intermolecular forces in the water itself because you're essentially breaking hydrogen bonds in the water. That would be endothermic, breaking a bond, but you're also kind of adding in these new interactions with the ions and the charged ends of water here. And I drew it the wrong direction because technically that would be the positive hydrogens. This is the negative oxygens. It should be flipped. That's okay. Okay, so because you're adding in these new attractions here with the molecules, that means that there is a release of energy in forming these new bonds, so to speak. These are really more attractions here, dipole-dipole attractions. So again, this one's a little bit harder, and I understand that that was a lot. I tried to give feedback written in your documents for each one of you, and you're welcome always to rewrite, resubmit anything that I give you and you want a better score on, but I hope that this helps you understand this at least a little bit better. I know that one was pretty hard, but good job overall. Come to office hours if you have questions, and I hope that was a little bit more clarifying.